It's my great pleasure to introduce Alec Jacobson, who's an assistant professor at University of Toronto. He is also a Canada Research Chair. Alec got his PhD at ETH Zurich, where his thesis won the ETH Medal and Eurographics Best PhD Award. His work ranges a lot of different topics, anything from fundamental questions about how to interpolate data on curved domains to novel user interfaces for geometric modeling. He's also made very significant contributions to practical software for geometry processing. The libIGL, which some of you may have actually used, won the SGP 2015 Software Award. And most recently, he's been doing a lot of really inspirational work on how we can take all the sort of academic algorithms for working with geometry and make them really work on real-world geometry for real problems. And so that's what he's going to talk about today.
So thank you all for coming, and thank you, Keenan Crane, for hosting me, and thanks to the other organizers of the Robotics Institute seminar. I'm very happy to be here and excited to talk about the work that we've been doing. So as we all know, we're living in the world of big data. We have amazing applications for video, image, speech, and text. And we're seeing these applications not just because of the wealth of data that we have, but because we're standing on top of a very mature history in signal processing, image processing, and video processing. And I'd like to argue that part of the reason we're not yet seeing these big data type of applications for geometry is that geometry processing is a much younger field. The idea of treating geometry as a signal that can be processed and processed digitally is something that we're still developing, and I'll show you some of the new research that we're doing in this area. And if we think in terms of big data, the access to these applications is not lacking because we don't have geometric data. In fact, we have geometric data all around us. So for example, we'd like to tackle our effect on the world's climate, and we can view climate data as scalar or vector fields defined on the surface of our planet. Similarly, if we look at self-driving cars that have been in the news a lot lately, the self-driving car, to operate efficiently and safely, needs to be intimately aware of not just the static geometry of the scene around the car, but also the dynamic geometry of passing cars and pedestrians. In medical imaging, we use curved surfaces, solids, and curves themselves to represent anatomical data. And here's an example from a telesurgery robot. And for this to happen in the real world, we're going to need to give that robot the information in real time, up to date, of that specific patient's anatomy as it's being operated on. We also see applications where geometric data is coming at the consumer level. So we have now cheap depth sensors that are enabling applications such as virtual try-on, where someone will stand in front of a camera and see a garment displayed in real time on top of their body. And of course, in advanced manufacturing, you have great improvements in terms of 3D printing technology. Here you see an example of a 3D printed prosthetic leg and a shoe from New Balance, where the sole of the shoe has been 3D printed. And the bread and butter of computer graphics, which geometry processing is sort of born out of, is computer video games and VFX. And if we look at games today, we're seeing increasingly cinematic and beautiful renderings that are happening in real time for the games. And for visual effects, these are now just as common as a camera or a boom mic. Even sitcoms or television shows are using virtual effects instead of going out and filming in live action. And we're seeing really interesting things done in cinematography for dramatic films, not just blockbuster type of movies. So all of these different applications require collecting geometric data, processing that data, and putting that geometric data to use in one way or another. And we put this all together. Traditionally, then, we think of the geometry processing as a pipeline, where it starts with acquiring that data and then funnels through various different stages of analyzing the geometry, editing or transforming that geometry, and then finally consuming that in one way or another. If we idealize this, then we can actually realize it in terms of a flow graph type of programming setup. So this is an example of a tool from a startup that I work with in Toronto that has created little modules that you can connect one output into the input of the other and create applications. So this one, for example, is for dentistry type of application. So this is if things are working well. In reality, when we're working with real geometric data, this pipeline is leaky. And we have leaks potentially happening at every stage of the pipeline. And these happen for a variety of different reasons. So the output of one algorithm might not be the right representation to be the input to the next algorithm. So we have a lossy conversion process where we're losing information. The output might be corrupted, or it might need to be fiddled with by an actual human user that requires manual intervention before we can fit to the next phase in the pipeline. So this breaks our automatic flow and slows down the entire process. Probably the most frustrating thing that can happen is you get data almost all the way down your entire pipeline, and then the last part fails, and there's no hope of getting it to that very last stage. So we have this lost cause. We get almost all the way there, and then we have to go back to the beginning and start over. And finally, I might point out that some things do actually make it out, and this might give us the false impression that things are working out well. And I'd like to argue that, in fact, this is a lot harder, and we have many more failure cases than we do survivors. And so to attack this problem, I kind of changed my philosophy about geometry processing. I see geometry processing as a subfield of biology. So in biology, you study the lifetime of plants or animals. In geometry processing, we'll study the life cycle of a shape. So we say that a shape is scanned from a physical object, or it's modeled by someone on the computer using some software, maybe like Autodesk's Maya. And then it goes through various stages of life. So it might go through deformation and decimation or a smoothing stage. We might analyze it in something akin to a Fourier analysis. And then finally, well, we don't like to say that the shape dies, but the shape is consumed in one way or another. So it might be that we render it into a film for a computer animation. It might be that we fabricate it using 3D printing. Or it could be that the consumption is making a decision. Is this bridge going to fall over or not? So viewing geometry in terms of the life cycle of a shape, now we should revisit and be suspect of conventional assumptions that we make about how we are going to structure our algorithms that operate on geometry. So here are a couple examples of common assumptions that we might make when designing geometric algorithms. We might say, OK, I want to solve this problem. Well, I can just use whatever type or resolution of geometry will make this problem as easy as possible to solve. Or you might say, I know the geometry for certain. And this means I'm able to do integrals or other things directly on that geometry, because I know with 100% certainty even where that geometry is. These conventional assumptions make problems easier. This is why we do it. They make problems mathematically well posed, and they often make it simpler to solve. So let me give a couple examples of how this might play out. So you might say, OK, I'd like to build a multi-grid hierarchy. So this should be a course-defined hierarchy of representations of our shape on the computer. In this case, I'm going to represent an octopus shape. So if I allow myself to assume that the geometry is representable at the coarsest level, I say, well, that's my octopus. And then if I want to create a course-defined hierarchy, I can just subdivide this octopus, right? So this is very easy. I'm done. Multigrid is solved. But in reality, your octopus is already given to you as a complex, interesting object. That's why we probably wanted to use multigrid in the first place, because we had a very high-resolution, detailed shape. So typically, the problem that can show up in practice is we're given the fine domain, and we want to figure out what is the hierarchy that makes this efficient multigrid solver work. So this is an example of one way to construct a fine to coarse hierarchy where we envelop a fine geometry with coarser and coarser cages that go around the shape. You know, geometry is inherently more difficult to work with than images, and often we can turn to images to make our lives much easier to work with. And some of the things that we can do with images these days are really astonishing. One of my favorite examples is from the machine learning literature, and that's the adversarial attack. So here, what we've done, or what the authors of this work have done, is they've taken a classifier that correctly identifies the image on the left as a panda, and they've added just the right type and just a small amount of noise that causes the classifier to incorrectly see this image as a gibbon, a type of monkey. And to a human observer, of course, that still looks like a panda. There's no way we would ever misclassify that. And yet, Ian Goodfellow, the first author of the original work, has now identified 3 years later that essentially what we've done with these adversarial attacks is we've created a specific type of toy game, a sort of academic game of manipulating an image that isn't really based on how images are acquired or even how images are perceived. So instead, what maybe we should do is look to how are images actually formed. Well, they're formed by light interacting with geometry. So we could instead create adversarial examples or attacks by manipulating those primary degrees of freedom directly. So in this example, what we've done is we've rendered 3D geometry of a stop sign. That image gets correctly classified as a street sign. And then we've manipulated the geometry now in a very specific and small scale way so that the classifier is fooled into thinking that the shape is something else, in this case, a mailbox. And if we sort of magnify the deltas or the changes that we're making in the image space, we can really see that when we make manipulations in the image space, these are potentially incoherent. They really have nothing to do with the underlying geometry or light that's creating the image. So these are two examples of manipulating the image pixels directly. And here's what we get for the same measure of pixel change in terms of the change measured on top of the image when we adversarially attack the lighting of the scene. So here we're making all the pixels a bit more blue, or here we're adding perturbations to the geometry. So these, because they're built off of those primary representations, geometry and lighting, we're getting a much more coherent or plausible change to the image. Now stepping back to our conventional assumptions that sometimes make life easier. Sometimes the conventional assumptions can actually make a problem harder. And this can lead us to a little bit of a trap. So here's an example where trying to isolate a particular subproblem can actually make our life more difficult and harder to achieve robustness. So consider that we'd like to solve some partial differential equation on this solid geometry. It's a microscope that's been modeled out of unioning together 24 different solid pieces. So if we follow the traditional pipeline, what we'd say is, OK, first step is discretize the domain. So we're going to discretize the union of all of these shapes, and then we're going to apply the finite element method to solve our partial differential equation. If we do this with standard tools, we'll get something that looks like this. There's a couple different problems with the solution. One is the lens of the microscope has actually been fused to the base. There was a tiny gap there, but our discretization software has actually merged them together because the tolerance is too low. The other part is we had very thin geometry, and this part wasn't recovered during the discretization. So we're actually seeing the shape sort of fracture apart there. And of course, the solution to our PDE has been destroyed because we started with a very bad discretization of the shape. So if we zoom out and we view sort of the life cycle of this entire geometry, you can say, well, I'm not forced to solve the PDE directly after discretization. What I can do is I can instead discretize each volume of those 24 pieces independently, and then couple them together and solve the PDE in a joint way across all of those different domains. And here we get a solution like this. We see that the solution on the base of the microscope is not talking through the lens because they're not fused together. So my approach to tackling robustness in geometry processing is to return to the fundamental questions that we can ask about geometry, and then consider how do we generalize them to messy shape representations. How can we ensure that they gracefully degrade when our shapes become messier and messier? So some of the questions that we've thought about are simple things like, am I inside or outside of a given shape? What is the combination of two different shapes? If I have the boundary of a shape discretized on the computer, can I also discretize the volume inside of the shape? Now, if the input geometries are very clean, each of these is actually a very simple problem. And we could all sort of sketch out solutions to these problems. But the messier that our inputs become, the more robust our solutions, the more intricate our solutions should be. a lot of these problems come back to a sort of fundamental paradox within computer graphics, which is we can often get away with very poor representations of our geometry to just visualize the shape, to create a good visual appearance of the shape. The same representation is actually not good enough to do geometric computation. This is for a variety of different reasons. If we look at a triangle mesh representation of a surface, we might have problems where there's self-intersection, so two parts of the shape are actually occupying the same place at once. We might have what are called non-manifold edges. So this is where you have multiple surfaces coming together along a shared curve or along a shared edge. And then we might have, oh, excuse me, we might have open boundaries. And so nobody wants this to happen in their PowerPoint presentation, but we also don't want this to happen in our geometric algorithms. Unfortunately, this is sort of the policy that we traditionally have. It's garbage in, garbage out. So if you have a bad surface representation, well, what can I do? You gave me garbage, my program will just crash, right? And we're probably all familiar with this. We pass in some geometry. It looked fine when we opened it up in MeshLab, but then when we gave it to our algorithm, we just got segfault or something to that effect. And this severely limits our applications. How can we ever build full automatic pipelines that go from acquisition to consumption if we have this sort of behavior in between? So our approach then is to adapt these traditional algorithms in theory to work even in the presence of messy data. So let's take one of those fundamental questions. Am I inside or outside of a shape? And see how this might play out. So we'll start with a clean representation of a closed simple curve in the plane. And we can say, OK, for any given point, figure out if I'm inside or outside of this curve. Now, we can probably think of various different ways of doing this. Maybe we walk in one direction and see how many times we pass through the curve, or we project on top of our point. But these solutions need to be adapted even if we start poking holes in the surface, we're missing data, or if we add sort of additional flaps of data sticking off of the surface, or even if we let the surface intersect itself. And even though determining inside or outside seems like a toy problem, this is really a fundamental problem if we want to solve larger things like doing simulation on volumetric shapes. So if I have a shape like this cat that has a design cut out of the side, I'd still like to be able to simulate it. And to simulate it, I need one of these volumetric tetrahedral meshes, so we're filling the inside with tetrahedra. And for that, I need to know where should I put the tetrahedra, what's inside and what's outside. There are previous solutions that look at this problem, but they're unsatisfactory in a variety of ways. So one way that we can try to do this is to solve this by instead looking for a function defined on space where the zero level set, wherever the function is zero, lies on our surface. And we can build this up as sort of an interpolation problem. We have a lot of data of what's on the surface, and we'll try to find a function that's zero on the surface, and let's say negative inside where it's blue and positive outside where it's red. And you'll see one of the issues here, if we look at the input on the left, as this function tries to ensure that the entire black part is on the zero level set, it has to oscillate up and down. Because we're looking for a smooth function, there's no way to approximate this zero level set without wildly oscillating. And what that gives us is these extra little loops that weren't actually present on the original data. So we've invented new parts that are considered to be on the surface that are solely due to the fact that this function is oscillating up and down. So we might think, OK, this function's oscillating too much, so let's put a smoothness regularizer on it. Let's try to smooth it out and damp out these wild oscillations. But unfortunately, then the price that we pay is that we can no longer perfectly interpolate our input data. So we've gotten rid of the oscillations, but now we've blurred the boundary of where our shape is. So we've lost information in this conversion from an explicit representation of our shape to an implicit representation of the domain. Another thing we might do is we might shoot rays. And if you shoot a ray through a clean shape, you can count the signed number of crossings to tell you whether you're inside or outside. But for a messy shape like this, you might get really unlucky and shoot through one of the holes, and then you'll get the wrong answer. And here I'd like to point out that it's not like you're getting the wrong answer with a fractional value. You're getting a dead wrong answer. Like no one would ever say that this point is definitely outside of the shape. But if you shoot your ray through the wrong part, you'll get completely the wrong answer here. So instead, what we're going to do is look at the clean example and see how can we generalize this to a messy shape. And the formula that we started with was this classic definition of something called the winding number. So a fairly simple integral. The idea is for a query point, the yellow point here, we're going to draw a unit circle around this point. And now what we're going to do is project the curve onto this unit circle and add up the signed length of that curve on the unit circle. So for a point inside of the shape will wind about that point exactly once. And for a point outside of the shape, remember we're adding the signed length. So any positive amount that we add up gets canceled out by a negative amount going in the other direction. So this gives us a winding number of 0 outside of the shape. And maybe it's worth pausing for a second to like sort of enjoy the beauty of this mathematics. We've taken a continuous integral, and it's outputting something very discrete. You're inside or you're outside. The winding number already correctly identifies a number of different scenarios that might happen in practice. So we might have nested geometry, and we'll correctly identify that we have a cavity inside of this geometry as long as it's oriented correctly. It will also identify parts of the shape that are flipped inside out by giving a negative winding value there. So we get a -1 inside of one of the lumps of this figure 8 shape. And then it will identify parts of the shape that are in some sense twice inside of the shape. If we think of this as two arms sort of overlapping, then that yellow point that says 2 is inside one part and also inside the other part. And accordingly, its winding number value there is 2. And we can actually consider this entire slide as one big shape with multiple components, and all of these winding number values are still correct. So then our idea here is quite simple in retrospect to say, OK, well, who said that that integral has to be over a closed curve? What if we just evaluate this integral even if the input is an open curve? And what you get is no longer a piecewise constant winding number value. You get a smoothly varying field. And this field corresponds in some sense to how likely you are to be inside or outside of the shape. And as we close up this curve, we see that it gracefully tends toward this perfect indicator function. So we see in all of the examples, the winding number is close to 1 when you're on the inside of the curve and closer to 0 when you're on the outside of the curve. You can see that this also handles multiple overlapping components well. And one of the things when we were first researching this was trying to understand, well, what can we say about this function? It's nice that it looks very smooth and it looks like it's gracefully degrading, but can we somehow prove that it won't have these nasty oscillations that we saw before with the interpolating functions? And what we did is we turned the function sideways. And when we looked at it like this, we just said to each other, OK, this has to be a harmonic function. We've looked at, in computer graphics, we look at harmonic functions all the time. So we're saying just by eyeballing this, this has to be a harmonic function. And we're able to prove afterward that indeed this is a harmonic function. The nice thing about harmonic functions is that they always achieve their maxima and minima on the boundary of the domain, in this case, the input geometry. So we can prove that there will never be some bump that appears later on in the shape. And so here we have a very clear delineation between the part of the shape that's outside and the part of the shape that's inside. Discretizing this integral turns out to be very easy. In 2D, we're just adding up the signed angle of each segment created by the point that we're querying it at. In 3D, this generalizes from angle to solid angle. The solid angle is the signed area of the projection of a triangle onto the unit sphere at that point. And then to evaluate the winding number, we add up the signed angles or signed solid angles for all of the triangles in our shape. Here, what you're seeing is messy geometry of a woman's head. So there's eyebrows and eyeballs and the mouth are all different components sort of laid on top of each other. And you're seeing in this volumetric view a slice through the winding number field. And when it pauses on the mouth, you can see that the inside of the mouth is being correctly identified as being outside of the geometry or the solid volume of the head. We can now feed in this winding number field to tetrahedralization software that can then discretize this volume. So yellow means we're inside of the shape, and otherwise we're outside of the shape. And these kind of tetrahedralizations are then used downstream to do more high-level processing, like structural analysis to see where something might break, or to do, this is an interesting example that came out of the lab that I was doing my PhD at. They optimize a shape so that it can balance precariously on a very small support. So this horse can balance perfectly on just one leg. Recently, in this past year, we've further generalized the winding number from triangle meshes, where each triangle defines its contribution to the winding number, to point clouds. And this nicely unifies the representation across various different messy ways that we can describe a surface, and then feeds into a variety of different output utilities that we can do with that representation. So by interpreting a mesh, a triangle soup, or point clouds in terms of their winding number, we can mix and match these inputs to various outputs. So I think maybe the best example of this is how we connect to 3D printing. So the typical 3D printing process requires that you load in the geometry as an STL file. Well, this is just a triangle soup file. Break up your surface into a bunch of triangles. Well, if you started with a point cloud, this means you have to first convert your point cloud into a triangle mesh, so then you can pass it to the 3D printing software so that it can slice it and design the tool paths. Well, what exactly is slicing and designing a toolpath? Well, really the fundamental thing is figuring out where you're going to squirt the goo, right? And you want to squirt the goo on the inside of the shape. And what is the inside? Well, the inside is the part where the winding number is closer to 1. So really all we need to be able to do is on some plane determine what is inside of our shape and what is outside of our shape. And this is exactly what the winding number does. And since we've generalized it to points, now what we can do is we can directly print a point cloud by just adapting the 3D printing software to read in on each slice the winding number field rather than having to cut through a triangle mesh geometry. So here's an example of one of those prints. So the input in this case was a point cloud, and the output here is our sliced and 3D printed geometry of that swan. Similarly, by looking at the winding number, we're able to abstract away higher level algorithms from the actual representation. And this is helpful for situations where we don't really need the user to care about how the geometry is represented. So one of the examples that we looked at was VR painting. So if you've used one of these, you have sort of these styluses in your hand, and you're waving them around. You're kind of just creating oriented ribbons in space. Or you're painting things by laying down these ribbons. So as an example of this, we thought of, OK, what if you went into a museum, you scanned, made a point cloud of your favorite sculpture. We only realized afterward that this is actually a sculpture of John the Baptist's severed head on a plate. Not, but maybe forget that. So you have your favorite sculpture as a point cloud, and you've gone into VR and you've sculpted a pedestal that you want to attach it to. And we can overlay these on top of each other. But actually, because of the winding number that's shared across point clouds and triangle meshes, we can even conduct their union just directly on these representations. We never need to translate them to any other representation. So we can cut apart the points and the surfaces that don't belong to the surface of the union just by testing inside and outside. And then we can send this union representation directly to our winding number printer, and we can get a 3D print that looks like this. So you might be wondering, OK, yeah, if you make a shape through VR painting kind of environment, of course it's going to be very messy. But For the kind of models that people are really creating using traditionally modeling software, how many of them are really messy in this sense? So we collected a data set of 10,000 models designed for 3D printing and that were successfully 3D printed. And we determined by the sort of the standard metric of what's considered to be a clean model, a watertight surface without self-intersections, only about 50% of these are clean. Now, then we looked at the winding numbers of these shapes, said, can we invent a new definition for clean that is a broader set of these shapes, but still lets us reason about the shapes in a very precise way? And we looked at, remember in the clean setting, the nice thing about the winding number is that it was piecewise constant. That told us we're dealing with a nice closed shape. And actually, it turns out if you look at this big data set of 10,000 shapes, about 8,500 of them are clean in the sense of they define a piecewise constant winding number field. So they're actually almost there, but they have other messy parts of their combinatorics, or maybe their edges don't zipper up perfectly as they should in a triangle mesh. So they might confuse traditional algorithms, but they really do define something that is meaningful in a mathematical sense. So with this new concept of a piecewise constant winding number field, we were able to design a Boolean algorithm that allows us to union, intersect, and take differences of shape in a robust and precise way that we can prove will be correct no matter what the input is, as long as it's piecewise constant winding number. Now, it's kind of surprising that in 2016, there's a new Boolean algorithm, because actually, Booleans have been used long before computers. So there was a great exhibit at the Sagrada Familia about how Gaudí was using Booleans to design the capitals at the top of the column. So he was really modeling with intersections and differences of ellipsoids and things like that. So many years later, the way that we achieved this is by using careful but broader preconditions on the input, and then being sure that we're actually achieving postconditions on the output. So being careful about what exactly can we say of the output of our geometry. So if we look across the 8,600 models in our data set, our method is, well, the first thing you want in a method is that it actually produces an output. So it 100% of the time produces an output. And then we're able to show that it's producing outputs that are meaningful in the sense that they don't have open boundaries and other problems such as self-intersections. And if you look across the state of the art, first of all, not all of these methods are even producing an output for all of these geometries. And many of the outputs are broken in some sense, that they might crash whatever downstream applications are running afterward. And as I've said a couple times now, maybe the most pressing downstream application is doing some kind of solving of partial differential equations or physical simulation our geometry. And for this, we require not just a good surface representation, but also a volumetric representation of the interior of our shape. And then we can proceed with a physical simulation like the bending of this bolt. So why is it that tetrahedral meshing is hard, especially in the context of computer-aided design models? So here's an output, a faceted output of a CAD model. And let's look at a couple of the problems here. So if we zoom in here, we might see messes like this. So we zoom in on this one. Pieces are coming together. This model is actually piecewise constant winding number. But we're seeing that we're really zooming in and seeing a mess here. And this one is my favorite. So keep track of how many times we're zooming in. So we could ask the mathematically well-posed problem, give me a tetrahedralization of exactly this shape. And we'll declare robustness as long as the boundary is represented by this. But is this really what we wanted in this case? Probably not. Right? So really what we want is something that gracefully degrades, and we have control over how closely we're approximating the input. In this case, we really don't want to represent this in our tetrahedral mesh. Instead, we probably want something more like this. So we take as input a messy representation like this, and we get as output a remeshed version of the surface and a nice mesh of the interior, where we can then reason that the surface is matching the input geometry up to some small epsilon. And in this case, the epsilon is really small. It's something like a 1,000th of the bounding box diagonal of the shape. So you can see that sharp corners are met by our method just by keeping this epsilon very small. So there's nothing going in here and circling all of the sharp corners. It's just the only way to create a nice mesh here is to conform to all the boundaries and creases. In our work, we lean quite heavily on this data set and large-scale testing. So for this tetrahedralization software, we validated our results on all 10,000 models in this data set and used the generalized winding number to extract just the tetrahedra that are on the interior of our model. And you'll see if you look at a few of these, there's some very thin, intricate shapes here that we're able to tetrahedralize. Maybe now's a good time to point out that I and my lab are very dedicated to open source software. I host a number of different libraries online. The largest is the libigl software, which is a collection of a lot of different geometry processing algorithms in C++. The tetrahedralization software is also open source. We call that tetwild. And then the fast winding number code is located here, which you can use for fast inside-outside testing, but also super fast and robust voxelization of 3D shapes. I'm also a big advocate for open data. So this data set of 10,000 models you can find online. We call it Thingy 10K. My colleague James Joe has done a great job with the web interface, which I hear is very nice for prototyping. So what you can do is you say, OK, I'm not really interested in making it work on every model. I want to make it work on manifold objects that have one component but are high genus. So you can just type that into the search query, and you'll get, in this case, 500 or so shapes that you can download and try out your algorithm. All right, so hopefully I've given you a taste of how robustness can be important, and I give you the sense that possibilities for geometry processing are out there for us to grab. Maybe I'll make some concluding remarks to recap. So some of the things that I'd like to leave you with are that we should question common assumptions. So how are we actually representing a shape? Do we really need to translate from one representation to another? How can we rethink our geometry processing to reach more broadly across the geometry processing pipeline or life cycle of a shape? And then finally, we should lean more heavily on large-scale validation. We have all of these shapes. If we're working on automatic algorithms, we have no excuse anymore not to test on a large number of shapes and report meaningful statistics about what we're doing. Some of the future directions that I think are most interesting is to really take this, what I'll call full stack geometry processing, to the limit. I'd like to be able to do things like go out really into the real world, scan a bridge, and then be able to tell you with some measure of confidence whether or not this bridge is safe to walk across. So do physical simulation on the uncertain data.
We need that in Pittsburgh, actually.
Do you? And another hot topic, of course, is machine learning. So I think geometric machine learning can be pushed a lot farther than the current status, which is mostly doing classification on geometry. I've dipped my toes into this a little bit. Here's one example that my student Derek has been working on in the context of style transfer. So this is how style transfer works in the image space. So we have this image of a waterfall and this stylized image of this dog. Can we create a waterfall picture that's stylized like that dog? So what he's done for geometry, this should be a video. Did it play? Yeah. So you have geometry as input and a stylized image, and then we can stylize that geometry all over the shape. So I think we can take this much farther, and this is really interesting in the context of generative modeling. So can we learn interesting things about geometry and then generate interesting new shapes? If we want to reach these big data applications with geometry processing, we have to embrace the messy data, and then we'll be able to tackle these problems with big, messy data. And finally, then I will say thank you to my colleagues, funders, and collaborators, and thank you all for your attention.
Okay, questions for Alec?
So you replaced a very inexpensive inside-outside test with what appears to me to be hugely expensive Why not do the simple test 5 times?
Yeah, so so this raises 2 good points. First is the naive calculation of this generalized winding number is O of n for each query. So we'd have to sum up the contribution of every single triangle. When we first looked at this problem, we noticed an interesting thing that you can do to make this a O of sort of square root n log n algorithm where you divide the shape up into little pieces. This will give you the exact winding number for much lower cost, but still pretty expensive, because if you think of a normal query as being closer to constant time. This past summer, we applied the Barnes-Hutt tree search method, which is similar to the fast multipole, or it's a precursor to the fast multipole, that makes this much, much faster asymptotically at the cost of doing it with a little bit of approximation. So that's what I would advocate for now. Now, the second interesting point is about the voting. So why don't we do this ray shooting and parity counting and just average them together? So it turns out that this generalized winding number is the solution that you get in the limit of doing an infinite number of ray casts. So it's the limit, this integral you can flip inside out and just treat it as shooting an infinite number of rays to get this solution. So that they are the same. The downside, maybe I have a secret slide. Let's see. Yes, will it show? Right. The problem with this kind of ray stabbing approach is that you can still get the answer wrong. You'll still get a noisy solution. It's going to be noisy exactly how rendering is noisy. So if you've seen a ray trace image that hasn't yet converged, you know that it can have speckles. And the speckles can sometimes be very bad, because if you're doing this a lot, you're bound to hit those unlikely cases at least a couple times. So what that means is that you get speckles on the inside where you really have no reason to be wrong here, but you're getting it just by being unlucky. So then you'd have to add onto your pipeline like denoising on top of that. Whereas here with our fast winding number, we don't have this kind of approximation. We have a much more controlled bias in the approximation. In the limit, they're the same.
Other questions for Alec?
When you say in the limit they're the same, can you get an intermediate result where you don't do exactly the winding number computation that approximate shooting a finite number of rays?
In what sense? So
you're saying that the winding number corresponds to shooting an infinite number of rays.
That's right, yeah.
So if I say I want to shoot a finite number of rays, is there something that corresponds to that with the winding number?
Ultimately, you're approximating integrals by sampling. You're just asking a question, how many samples do I need?
Yeah, so I looked in. I didn't look at it back in the context of like, could we redo this like triangle summation to get the same error as a finite number of samples? But I did look at like in statistics, you have this idea of like knowing when you can stop your study because you have a statistically meaningful result. So I was looking at this as trying to like salvage the ray stabbing approach to say, okay, can we shoot a number of rays and then we can say with such and such certainty I'm happy with my solution so far. I think you could do something like this. I should say, by the way, if you just grab a ray tracer off the shelf and use it for ray stabbing, even for clean geometry, you occasionally get the wrong result. And you get the wrong result by an integer value because your ray like slipped through an edge and didn't get counted, or it hit the edge twice and didn't. So in terms of just pure robustness of the fundamental pieces, ray stabbing is actually kind of hard to do. You can write it robustly, but it requires much more intricate and slower numerics than what's typically used in like a rendering raycaster.
Other questions? Yeah, Chris.
I would argue you're trying to fix something at the wrong level. It seems to me what you want to introduce is a semantics on shape, particularly about whether a model is watertight. Or particularly, I have two parts that I'm butting together, and I should tell it symbolically, these are butted together. Particularly, for example, you want to model one of these cups and one of the plastic tops, and you deform it on, and you might have an O-ring that's permanently deformed.
That's right, yeah.
I don't see how you could possibly answer questions about physics by just playing with triangles. You have to have semantics.
So in the one sense, I totally agree with you. Like if we could rewrite history and say like everybody should have created geometry this way, then I would be like, yes, we definitely should do that. The way I kind of view this is like the geometric data that we're creating at an outrageous pace right now is like a natural phenomenon that I don't really have control over. And I need to design geometric algorithms that work, even though I don't get to say like, hey, you shouldn't have created it that way. You should have added all of these semantic layers on top of it. I definitely agree that it would be nice if all of those were in place, but I don't think it's as simple as like walking down the street and telling Autodesk like, hey, you forgot like to add a coplanarity checkbox to your meshing software, and that would like fix all of the problems. So on the one hand, I agree, like, yeah, it would be much better if we had a richer representation of the shapes, but the like interesting reality to me is that we don't, and we're trying to make the best that we can with what we have.
But shouldn't these geometric algorithms be simultaneously reasoning at a symbolic level?
Yeah, so I think this is really interesting. So what I would like to do then is argue about these symbolic representations in a way that accounts for uncertainty. So even though we don't have that explicitly modeled here, we can say with some fractional value, I'm fairly certain that these things are at resting contact, for example. So like, given the example of like rigid body simulation, most of the simulations work by modeling instantaneous contact, and then a switch flips when they are representing rolling or resting contact, right? So it might be interesting to revisit these in terms of percentage values. Like, are we 100% certain that this is resting contact, or can we transform this into a measure of confidence?
Well, the other issue is that you put something on top of something else, and over time it creeps because it's really...
That's right. Yeah, that's right. Yeah, you get this sort of like ice rink effect that things like jitter and slip about. Yeah.
Other questions? Okay, I'll ask one.
Sure.
So how about kind of going the other direction of Chris's comment, I think a lot of people in here, for instance, would say, why are you working with meshes? This is like, haven't meshes gone the way of the dinosaur? When we deal with geometry and vision and learning, we use point clouds and voxel grids. And if you wanted to decide whether that bridge is gonna fall over, just do something end to end, and don't try to pick the representation. Just let it be learned. So I mean,
I see. So like, yeah, like.
A lot of your problems just come from working with meshes, and shouldn't you just stop working with meshes altogether?
So in some sense, we should be careful. Like in the 3D printing is an example of like, I really think converting it to a triangle mesh was like completely unnecessary. This was like a file format and an API issue, and not really a representation issue. Triangle meshes are a really nice representation and a really efficient representation for certain types of surfaces. That's going to be hard to deal with in an efficient way if we're just looking at points that don't explicitly represent the topology, or voxel grids where either we have to pay the cost of the sort of annoyance of working with sparse voxel data or octree data, or working with very dense amount of a full voxel grid. So I think triangle meshes do play a role here, but I certainly wouldn't say like, all right, like you've heard this talk, like go out there and use triangle meshes for everything. Indeed, it will be, like we have some progress now in geometric learning of how do we do things like convolution on these shapes in a context that works for machine learning. It's nowhere even close to how well CNNs work for images. So yeah, there is like a temptation to just say, let's just throw it all away and use 3D images. I'm not quite ready to agree with that yet. Thank you.